One. Good morning, afternoon, and evening, everyone. Thanks for joining us for another Data Engineers Lunch. This is Data Engineers Lunch 86. Today we have a special guest, Thomas Neubauer. I hope I said that right, Thomas. Please forgive me if I mispronounced that. But we'll be going over building real-time applications at scale. It's going to be a case study in Cyclist crash detection. Pardon me. The co-organizers for this event, Raul and myself, we are looking for speakers and sponsors for this event. If you're interested in either opportunity, please reach out to me at the email listed below. We are a part of Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. We are a part of a larger community called Data Community DC, and that's made up of a large of different groups generally focused around data. You can find out more about these groups of the emails and addresses listed below. What do we cover here on our Data Engineers Lunch? If this is your first time here, we cover everything from the ingress and egress of data and everything in between. We cover everything from databases, ETL, and all the tools and processes in the data engineering world. So if this is your first time, I'd like to thank you for joining us. It looks like I've lost my screen. To bring that back up. Again, looks like I lost my audio as well. Should be back now. Sorry about that. Let me go ahead and share my screen and we'll get back to it. All right. There we go. Let's give that a quick second. Let me go. Welcome. And finally, here we go. If it's your first time here for the lunch, please introduce yourself, how you found out about our Data Engineers Lunch, what you're hoping to gain from this lunch, and any future topics you'd like to hear about in the future. Group rules, like I mentioned earlier, please be polite and courteous to others, especially our speaker. If you have a question, ask it. We are trying to build a community here, and obviously we want you to share what you know with us. Here at Anant, we build and manage global real-time data analytics platforms surrounding Cassandra, Spark, and Kafka. I'd like to take some time to thank our program sponsors, our organizational sponsors listed below. 15-second announcements. If you have any jobs, meetups, hackathons, conferences, or classes, please leave a comment in the comment section with a short description and any links related to that. We are hiring here at Anant, part-time and full-time positions. If you're interested in any of these opportunities, please visit our website listed below. We have our future events coming up. Obviously, we have our Data Engineers lunches every Mondays. We have our Cassandra lunch coming up on Thursday. I'd like to point you to the SLA-DB Summit coming up mid-February, February 15th and 16th. That is online. Please register today. And then finally, our latest edition for our Apache Cassandra runbook is out. Please download your version while it's still available. And with that, I'll hand it over to our speaker for today. Over to you, Thomas.
Thank you very much. Thank you very much for the introduction. So I'm going to share my screen and hopefully it's going to work. Cool. So hopefully you can see my screen. If you can't, please shout. So today I want to talk about building real-time applications. Particularly, I want to talk about how to involve a machine learning in real-time pipelines. And so a bit about me. I'm Thomas Neubauer. Currently, I'm CTO and co-founder at Quix. And I want to talk about my experience from my previous jobs, where I was building real-time applications, which was in McLaren. So in McLaren, I was leading a team that was connecting F1 cars to the cloud. So the people in the factory can build real-time decision insight that the people in the garage would use to use different tires or change the settings of the car. And I'm mentioning this because it was actually quite challenging streaming use case. The car were emitting a lot of values, around 30 million different numbers from different sensors per minute. And some of the sensors were really high res, like 1.5 kilohertz. So you're getting 1,500 different floats, different numbers per second. And in the factory, we had a truly cross-functional team, ranging from data scientists, ML engineers, mechanical engineers working on a chassis and aero, simulation engineers, etc. And that combination of a streaming use case and this type of roles in the team really created a challenge. So we quickly find out that even though we connected cars, and it was quite a software engineering job, but still, we connected the cars using Kafka into the cloud, and we thought that the job is done. But unfortunately, people couldn't really reach and access the data in the broker. And we needed to teach everyone how to do it, and it was quite painful. So this is where the idea really starts to grow, that there is something that could be done to kind of make the streaming a bit better for data teams. So I'm gonna skip that because we can't do it here. So first, I want to just mention a bit of difference between batch and streaming, because maybe some of you never work with streaming. I'm not sure. I usually ask in person meetup, but here I assume that some of you don't. So the thing is that with a batch, you're working on data under your under your fingers. So you have table or any sort of structure where you perform your operations. With streaming, you get continuous data flow where you have to process data piece by piece. And that actually gets quite difficult to get a head around when you need a stateful processing. So for example, imagine you calculating a rolling window of some sensor for last 5 minutes or last 60 seconds. With the historic data, that's quite easy. You're just calculating the rows and cells. But with the streaming, you have to aggregate sum and count. So every time you're calculating this value, you do sum divided by count. So this is a completely different approach to a quite common operation like average. So when you're building streaming application, there is two different approaches, mostly two different approaches. So the number one is you use some broker, like for example Kafka, but you can use Pulsar or others, and you use produce and consume API client libraries directly. So if you go to Google and you Google Kafka Python, you would get like 2 or 3 different client libraries that allows you to read and write messages from and to broker. So you can use them, or you can adopt stream processing framework, like for example Apache-Link, Spark structured streaming, or data flow with Apache Beam. There's others as well. Now, what is the difference between those two? Well, the first one, it's very elegant. It's lightweight. You don't drag any dependency with you, so that's cool. You have plenty of different languages to choose from. You have no dependency on JVM in your code, and it's relatively fine for exactly one message at the time processing. So what that means? you're processing messages independently on each other. So you don't need any state, and you don't need any dependency on previous message. Think of it as you have fraudulent operation detection in a bank, and you train the model to detect if the transaction is fraudulent, and you don't care about the previous transactions. Every transaction is atomical decision to be made. At that point, this approach is quite cool. The problem gets when you try to work with the data, not messages. When you actually want to see through the messages to read data, like calculating average, rolling windows, merge streams, do group by, things like that. This is obviously where you get tempted to use something like Flink. And Flink would solve that for you because these stream processing frameworks have these complex operations built in. The problem is that by moments you bring in Flink or Spark into your architecture, you're increasing the complexity a lot. You have to basically run another cluster side by your deployment to run your stream processing code. Because with the Flink or Spark or Dataflow, you're actually not using your code to manipulate data. You're building a declarative code that you send to this server, and then the server-side engine would use it to run and distribute the code and data in a cluster. So basically, this technology is not relying on Kafka for scalability and resiliency, but its own orchestration engine. And that, unfortunately, brings some problems. So you have Java dependency because most of those technologies are in Java. So when you want to use it from Python, if you are, data scientist or ML engineer, it gets really painful. B, you can't use the classical developer tools like your IDE and debug line by line because the code is not running on your laptop. It's running as a black box in a Flink or Spark. You can't use typical tools like, for example, profilers, or you can't use you can't use the logging as you are used to. And the things get really complicated when you want to try to combine the old and new way. So imagine you have microservices with REST APIs and everything, and you want to attach your streaming code, your asynchronous code into these microservices. This is really why it's getting complicated, because you can't just take the Flink SQL transformation and deploy it to container. You need to run it in the Flink. So is there a third way? Well, we have found out that these limitations of stream processing frameworks were too much for us and we couldn't use it. But we also find that the pub and sub API of client libraries is not enough. So we have decided to build a stream processing library on top of the pub and sub API that would rely on Kubernetes and Kafka to deliver scalability and resiliency like stream processing frameworks, while keeping the advantages of the first option. So our approach is to combine these two technologies, actually three technologies, together. So Kafka, Kubernetes, and Python, because I don't think that Python really, the Java is a language for machine learning and data in general, and data teams have to use them just because there's no other option. So no Java and no SQL. There's nothing wrong with the SQL, really. It's just when you want to build crash detection, for example, and you want to use machine learning model, SQL language is just an obstacle. You want to use Python because this is where the whole ecosystem lives in, and you want to use Python libraries out there to help you. So putting a Python on top of SQL, it's just a problem. And you can, for example, look at the official architecture diagram of how Flink does that with their PyFlink library. So they obviously can't really natively support it because it's Java framework. So they have this Python environment that's communicating with the Java environment, and you can imagine that just debugging code in this environment is gonna be a nightmare. Yeah, so let's talk about our use case today. To build streaming processing pipeline that we're gonna build today, you need to really get under your skin this most important concept. Sometimes it's called pub and sub service, but basically it's a service that subscribes to input topic, transform the messages into something else, and publish the output to another topic. So in our case, we're gonna listen to sensor data from a fitness application. We're gonna call ML model inside this service, and we're gonna output there's no crash or there is crash. And here we're gonna rely on Kubernetes and Kafka to scale this processing and make it resilient for hardware failures, code failures, etc. So first of all, the way how we're gonna scale our application is to leveraging Kafka partition system. So you can create a topic with 16 partitions, for example, which means you are allowed to deploy your code up to 16 instances, and Kafka will redistribute the load evenly to those instances. There's a very important concept called message key that is basically telling you where the message will go in a partitions, and this is where we're using it to stick the streams on the same partitions and on same services. Now, if one of these services crash, they will get restarted because they're running in Kubernetes as a deployment. The moment it crashed, it gets restarted. If you have hardware failure in Kubernetes, Kubernetes will move the pod to another node. So this is where you have your compute sorted out. And in terms of Kafka, we will replicate the data between different nodes in a Kafka cluster. So if we have hardware failure in Kafka broker, again, the others will take the lead and make sure that our stream processing works. So this is how we're gonna leverage these technologies, so we don't have to build something like Flink, the cluster where we're gonna run our code. We can just write a Python, run it in our IDE, do line-by-line debugging, and be happy. And when we deploy it to production, we're gonna rely on these technologies to make it production ready. Cool. So before we jump to the coding part, just one mention about the ML deployment, because I'm sure that those of you that work on ML projects, you surely had an experience with working with API-driven deployment, where the model basically is deployed as a microservice with API in front of it, and you're calling the API with request, and then inside the model is called and the response is returned to the client. There's nothing wrong about this, except when you're doing this in a real-time application, you might get a lot of requests, and there is a CPU overhead between every HTTP call that you do. And I mean, here, for example, we're going to send 5 times per second data point for acceleration meter. And if you do that with REST API at scale, it's just a lot of CPU wasted on that. You're also introducing latency. That might be sometimes a problem. But the biggest problem here really is that if you don't scale your service enough and you get spike that you not anticipated, what's going to happen is that this service will just linearly get longer and longer to answer up to the point where you reach the timeout of your clients. And at that moment, you have disruption in your system, your application is no longer working, but also you're losing these messages that are just lost. And this is where Kafka really works well to help you with this by putting these messages into a queue. And so if you have less resources than you need, the worst case scenario, the answers will just come later with a bit of delay. And if you have any sort of downtime, you just fix your service and it would continue where it stopped. So you're not losing any valuable requests. Like imagine transactions slipping through the fraud detection just because the fraud detection model was down. That's not cool. So about the demo. So today I want to show you how you would build this simple application where we're gonna have a phone from where we're gonna stream GPS location, altitude, temperature, and G-force data, and we're gonna stream it to Broker. We have trained model to detect shaking, because I'm not gonna crash here in front of you on a bicycle, obviously. So we have adjusted this a bit. So it's gonna detect me shaking with the phone. And I have here a Jupyter notebook in Colab where if I go here to Quicks, I have here many different sessions where me and Javi were, walking over the stairs, walking, running, and then shaking to kind of create the data that we can label. So here you can see there's a 2-minute session, and I can get the G-force data. Well, maybe not in this one. I get another one. Actually, I can get the one that is now running. There we are. And then this is data that happened in the last hour. And it's just a table-like structure. And you can get it with one button to call up, and you can start training your data, which we did here. So here you can see that we have get some sessions. We labeled when it's shaking, when it's not shaking. And there is some data analysis of the data. And at the end, we're using TensorFlow in this case. And here we have backtesting of trained model to see if it's working on a different data set. And at the end, what is important, and this is the most important part here. We create a picker file and we publish it to a blob storage. Because we're gonna use that blob storage in our pub and sub service that we discussed before. So now, going back to here, I have my phone running, and I can start it. And the moment I start it, you see that this is getting green. And that's because we are starting to stream data. There we are. And if I click on this and I explore live data, there's a Thomas S20. And if I take the phone and I shake, you see it going up and down. If I put it back on the table, it will stabilize to calm. So our pipeline is working and it's running. And if I go back to here, I also created this super simple front-end application just to show you the result of today's work. So here you can see the phone, and if we wait a bit, it will happen. There we are. You see I'm in the Prague right now, sitting there in my home. Cool. So how we can build a pipeline that would real-time analyze this data and detect shaking of a phone. So going back, I'm gonna click on this and create a new node with the transformation. So there's a library full of different templates, and the template generator will build the service for you against your environment, so you don't have to, stitch it together. And this is a template for exactly the service that we were discussing in the slides, pub and sub. One topic in, some processing, and one topic out. So I'm gonna call this crash, or maybe let's call it actually what it is, shaking detection. And we're gonna output it the fleet console. Cool. So now we get the Git project with, the initial commit. And this is a function that will be spin up for each phone. So this is the way how we're going to scale this. And each class of Quicks function will deal with one stream, which means one phone. I could clone this locally, but I'm going to use this web IDE for today. So first, I can just press run, and this will print the data coming from the phone. There we are, timestamp and the team and more columns that are visible here. So if I, for example, go here and print what I'm interested in, so if there is a GeForce X in data frame, now you can see here that we're working with the data frames, Panda data frames. That's because we're trying to, with our library, abstract some of the complexity of stream processing under the hood to make it look and to have the interface that people are used to. So if there's a GeForce in it, I'm gonna just print it, and I'm gonna print X and GeForce epsilon. If I press run, there we are. So now you see it's a bit faster because it's catching up with the leading edge, and eventually it will get the moment now, and we can work with it. Cool. So well, how are we gonna get the model here? So I have here requirements.txt, where I'm gonna import a library called Azure Storage Blob. This is where I have my model, and I'm just gonna load this model to memory. And I'm gonna do that in main PI because I want to just do it once. I don't need to do it for every stream. So here, I'm just getting connection to that blob store, and I'm loading that TensorFlow model that we train in a Colab. And then I would just pass this to our function here, which we are running for each stream. There we are. Cool. So that's it. And now in Quicks function, just going to extend the constructor and initialize it here. And we are very close to be done. What we have to do now is calculate new column that this model expect, and we have calculated it here in this notebook. If there we are, GeForce total. So I'm just going to copy paste this. And for those of you who work with something like KSQL or any other in-memory database, you might be familiar with the problem of different SQL dialects, where you using SQL to get your training data and you're calculating your features, and different SQL for calculating the real-time features, like KSQL, for example. This is not the case. Python is the same in Jupyter Notebook like it's in this service. It's the same dialect of Python, it's just a Python. So that's the reason why I can just put it here. Then the second thing is I'm just gonna load the model. Sorry, load the model. Call the model with a traditional apply, well, not apply, but with the traditional way of data frames, how they're working. So I'm gonna create a new column where I'm gonna set the result of this model, which takes as input variables the GeForce data and GeForce total. And I'm just gonna print it to see that we are working here. So print, and this time I'm gonna print just the shaking. So let's see. Yeah, I'm missing my libraries for my machine learning model. So I'm just gonna paste here. Those of you who might be interested how this web IDE is working, well, it just spin ups a Kubernetes pod with Python environment in it for you, so you can use it. And then to the WebSockets, we do the autocomplete there. So this is now installing these two libraries. There we are. And if I go to Quix function and try it again.
So while that's running, Thomas, I wanted to point you to the chat. We've had some questions come in.
Yeah, let me open it. Question is how? Oh, there we are, chat. Yeah. So going from top, and we also use Amazon MQ or can we also use Amazon MQ or Google Pub and Sub? So, well, we have connectors for Pub and Sub, and I think for Amazon MQ as well. We also build the library, the open source library that I'm showing you now, to be broker independent. So in the future, we hope to build the Pulsar version and probably Google Pub and Sub version. But for now, the connector is the way to go. So you connect your topics into your Kafka broker, and then you put the results back with the sink. Then, are you using any sort of serverless package for Kubernetes to manage your Python processes, or did you wrap processes in your own process orchestration in the container? Yeah, so if I show you here, there's a Dockerfile that you get with the service. You can edit it as you want. Then we give you a Helm chart, and this gets deployed to our multi-tenant Kubernetes using our orchestration layer. So we manage your containers and the build process as well. So this code then gets deployed against the Git version. So we build the Docker image, we deploy it as a container, we manage the monitoring and everything. So there's a serverless Kubernetes under the hood of Quix. Which database type is best for streaming data plus analytics? NoSQL or classical relation database? It really depends on the use case. So when you're looking at the classical aggregations and standard filtering, the SQL-based processing databases could be quite useful, like Materialize or others. I think when it gets a bit difficult is when you need to use, for example, machine learning or some more complex logic. Like if you, for example, building a car simulation, the SQL probably gonna be not the tool for the job. In terms of relation databases, they have very poor performance and really not scaling well. So we tried some. We tried, for example, Timescale DB, and they have its own limitation. And I think in general, databases are not really well in scaling. They're not doing well in scaling. and you're gonna have to throw the money on them to solve any sort of real-time processing at scale. So this is one topic per phone, or is it multiple phones per topic? Very good question, important one. It is multiple phones per topic, but each phone gets binded to one partition in the topic. So imagine you have 1,000 phones, then these 1,000 phones will be on 1,000 different streams, and each streams, they automatically distributed over the partitions in the topic. And then you just scale horizontally your service that we just built together here, and each service would get a portion of these streams. So it's very important to follow this concept to build a scalable pipeline. Yeah, so that was last questions. If you have any more questions, I will just check this chat later to answer more. Cool. So here we have getting no shakes. So if I take the phone and try to do some shaking, I think I'm gonna, for the safety run again. Yeah, there we are. I'm not sure if you see, but now I start shaking and I'm getting 1. I stop shaking, I'm getting 0. I'm shake again, 1. I'm not sure if you see my phone. So there we are. So this service is working and is doing what we want. Now, we can consume this in the end application to show you the result. And we're gonna do that by just attaching this simple 3 lines of code, which is, if there is a shaking detected here, we're gonna create an event that we're gonna consume in that front end I showed you. So let's press run here. And if we go back to our pipeline, I'm gonna stop this front end. And I'm gonna change the topic it's used from phone data to fleet console, where we have the results of our model. So this is now running as a container. And now I'm gonna use this. And now, if I take my phone and start shaking, you see, crash detected. So this is how you can real time consume the results of your pipeline in your application. So now it's just the last step to finish the art, and that's going to be deploying this into production. And that's where a lot of companies struggle. So that's where a deployment comes into place. So I'm going to stop this code. And you see that I did some changes on the master branch. You should not do that, but for this demo, it should be fine. I'm going to create a Git tag of this code called v1. And I'm going to deploy it as a service with some resources. And now you will see that we're kind of plugging this service into this pipeline, where we're getting from phone the data here. This data is, there we are, you see the JSONs. This data is coming to this service, which is now getting built into Docker image, so it could run in Kubernetes as a container. And this data is now being consumed by the front-end application, where you might be asking how you do that. Well, there is a WebSocket interface to any pipeline you create with Quix. So we are using that in the front end. So there we are. So hopefully it made sense. I just want to say that our open source library is on GitHub, of course. You can get it from here with using this QR code. You can also sign up for the free Quix account if you want to try it with the Kubernetes. But the library is working out on its own. And we also have tutorial. If you go to docs.quix.io, where you can follow this exact process step by step. So you can build it by yourself, the same application. Everything I showed you today is in our open source library. So you should be able to build it from scratch. I'm going to check if there's any other questions. Yeah, there are. So can you share best practices on replaying event streams? Seems like state and storage size gets really hard to manage if you want to have a topic that can be replayed. Very good question. So we have done what we call internally a replay service, because basically replaying directly from topic has some limitations. Like, for example, it's very hard to distinguish what data you want to replay. You have to kind of replay the whole topic, which sometimes could be, you just interested in 1% of the topic. And also Kafka is really not a database, so querying capability are almost zero. So we have here, if I go, for example, here, you select the data in the store, and you press replay, and it would replay the data from a database that we have in Quix. You might be asking what this database is about. Well, it's a combination of 3 different databases based on what data you send, because we haven't found so far a silver bullet database technology to store time series data, binary data, video, and metadata. So that's why we combine different ones to one package. And then you can use it for replaying or training your models. Good, so no other questions. So I guess I will pass the stage to Akwe. Thank you very much for coming here. I really appreciate that you listened to me. And if you have any other questions or you want to chat just about streaming, write me on our community chat, which you will also find on quix.io. And we sometimes having different discussion about streaming. You will find it under the community. Thank you very much for coming here, and I'm passing the screen share.
Thank you very much, Thomas. Appreciate you. Especially since we know a little bit under the weather today. Thank you for toughing through that. We really appreciate it. I want to thank everybody for joining. If you haven't already, please like the video and subscribe to our channel. Also like to remind you to download the latest edition of our Apache runbook. It's available at anant.us/runbook. If you haven't gotten it already, it will be in the descriptions for this video. And we'll see everybody same place, same time next week. Thanks for joining, everyone.
Have a nice day. Bye-bye.